Hello students, this is Mr. Hart, and we want to start off our unit on stars, galaxies, and the universe. So there's a couple of things we need to talk about, and again these are just summary videos, so we won't be able to cover everything, but I want to give you a sense of what we talked about in class. So first of all, one of the things we did was we looked at this simulation that shows us a good scale of everything. The reason we want to do that is because we're trying to understand everything in the universe, and the universe is really big. So we need a good sense of how big these things actually are, because just stating numbers doesn't mean a lot. So if you want a good sense of how big galaxies and stars and all these different things are, go to this link right here and go through this simulation. You'll be able to slide and go to really big things and really little things and get a sense of how small we are in the universe and how big we are compared to protons and other things like that. Okay, so take some time to explore that. But once you do that, then you'll have a sense of where we are in the universe. Okay, everything and everyone lives in this universe, and the universe is really, really big. So welcome to the universe. Okay, a couple of stats just for fun. First of all, obviously the universe covers everything: time, space, matter, energy. There's all a finite amount of that in the universe, and the universe is all encompassing around all of that. Okay, we believe that the universe is about 14 billion years old. Okay, and that it's 93 billion light years across. Okay, so light can travel about I think it's like 20 million feet, or sorry, 20 trillion feet in a year, or something like that. It's ridiculous. And so that is how many times larger than the distance light can travel in a year. So if light can travel a couple trillion or quadrillion feet, this is 93 billion times larger than that. Okay, so it would take light 93 billion years to cross the universe. Okay, and then this is the one that blows my mind. There's approximately, they estimate, about 10 to the 80 atoms in the observable universe. Okay, so 10 to the 80, that's 10 times 10 times 10 times 10 times 10, 80 times. Or in other words, it's a 1 followed by 80 zeros on the end of it. Okay, that's the number that represents the approximate number of atoms in the universe. Okay, so it's a really, really, really big number. Okay, but before we continue on with this, let's go into a little bit of history here, because I want you to understand that it's not obvious that all of this is true, right? When you look up in the stars and you ask yourself what is out there, it's not clear that you're going to guess that it's a universe that's 14 billion years old and 93 billion light years across, right? Imagine that you lived thousands of years ago and you just looked up at the sky and you saw the stars. What would you think they were? What would your understanding of the universe be? If you think about it, back then, a lot of people thought that, the earth was flat and the stars were kind of a blanket above us that was to the heavens, right? And the gods lived up in the stars or whatever, right? So they thought the stars were just kind of this blanket of light, if you will, just above the earth. And even the Greeks, who had a good understanding of, what the planets were, and they knew the earth was round and did all sorts of astronomy. If you look at their original model, okay, they did have the earth at the center of the universe, which is very incorrect, right? But they understood what the moon was, right? Here's Luna, here's Mercury, Venus, Solus, that's the sun. They thought the sun was kind of like a planet and just orbited around the earth. Okay, Mars, Jovius, which is Jupiter now, and Saturn. Okay, they understood all the planets, but if you just go outside of that, they thought it was just kind of, again, this blanket of stars where all the constellations existed, right? That whole circle right there was just kind of, oh, and this is where the stars are. This is where these glowing lights are. And then the gods again lived past that, or whatever it may be. Okay, so it was very, speculative, often tied to their religious beliefs and other things like that. And they didn't have a good sense of the fact that stars are not just in one spot or a blanket. It took a really long time to actually realize that, if this is our solar system right here, right, this kind of represents our solar system, then the stars are not equally spaced from us. They're all sorts of distances away from us and distributed, okay? And so that picture did not develop for a long time, okay? And even when we started to get an understanding of that picture, that stars were not all the same size and not all on this blanket, okay, around the Earth, it took a long time to figure out, well, how far away are those things and what are they doing? Okay, so it wasn't until a man by the name of Edwin Hubble that we really got a good sense of telling how far away stars were. Okay, so he's a prominent astronomer back in the early 1900s. He's very famous for using these supermassive telescopes to look at the sky. You've probably heard of the Hubble telescope, which actually orbits the Earth right now. It's actually in space, but it was named after him because of all the research and stuff that he had done. And what he's really known for is kind of the system that we use today for determining how far away stars are. Okay, so how would you do that? How do you look at a light in the sky and say, oh, that's this many million or billion miles away, etc.? Okay, well, what he comes up with is what we call, well, first of all, he starts to look at what is known as the emission spectrum. Okay, so every element has an emission spectrum associated with it. So based on the color of the light that is, or the light that's coming in, we can look at the colors and see which colors are most prominent. Even if you look at like your ceiling light, it's probably a whitish or yellowish color. That's not just a single color, it's actually a combination of multiple colors that give it kind of that blend that looks white or looks yellow. Okay, so if you look at different elements that emit light, they'll actually have kind of these colored bands that are very prominent. And so based on those bands, you can actually tell which element you're looking at. So looking at stars, you can actually look at all the light coming from the star, look at the colors that are most prominent, and use that to determine the composition of the star. Okay, so he'd look at these emission spectrums, he'd look at the bands of light, okay, and he used that to determine the composition of the star. And based on that system, he came up with what's known as the standard candle. Okay, so there's a very common star that has a specific composition and a known brightness. Okay, so just like if you're looking at a candle, it kind of has a constant amount of light coming from it. Based on how much of that you see, you can kind of determine how far away it is. So he did the same thing. Edwin Hubble did the same thing, but did it with stars. If you have a compositional star that has a known brightness based on its spectrum, based on how bright that is in the sky, you can determine how far away it is. Okay, so he started looking at that, and that's the system he still uses today. It's obviously a lot more complicated and complex than that now, building on other things. It's called the cosmological distance ladder. But you can compare other stars to that and use that to determine how far away those are, etc. But it's all based on knowing these compositions. Okay. But something interesting was happening when Edwin Hubble was measuring these, okay, these standard candles. Okay, and to understand that, we need to understand what a Doppler shift is. Okay, so a Doppler shift is a change in perceived wave frequency because of the movement from an observer. That's a really fancy way of saying that basically if something is moving towards or away from you, if it's a sound, if like something is, making a sound while it moves towards you, it actually will change the pitch of the sound you hear or the color of the light that you see. Okay? So based on the movement of something going away or towards you or away from you, you can determine if the sound is going to go higher or lower or the color is going to shift to a different color. Okay? We don't have a lot of time to go into detail on this, but as a simple example, if you see a police car going down the street and it has its sirens going, if that police car is coming towards you, then the sound waves will be kind of compressed as it's moving, right? It kind of compresses the sound waves as it's moving along. So you actually hear a higher pitch, okay? And then if that police car is moving away from you, you actually will hear a lower pitch, okay? There's some material on Canvas that show this really well, some YouTube videos that show this really well. But that's the main idea, is waves change based on movement, okay? So what Edwin Hubble discovered is that a lot of the things he was looking at were redshifted. Okay, so for light, if a star is moving away from you, all the bands that you measure will get shifted towards the red color. Okay, The opposite of this is a blue shift. So if an object is moving towards you, all the bands will move towards the bluish and violet colors. Okay. So when Edwin Hubble was looking at most of these stars, what he found was that almost all of them were redshifted, which means almost all of them are moving away from us. This is kind of strange if you think about it. Okay, let's look at an example. If we're just looking at our galaxy here, okay, so this is supposed to be a representation of Andromeda galaxy and our Milky Way. I can't remember which one is which, but if this is the Milky Way, for example, our sun would be about right here towards the edge of a spiral. Okay. And so if you think about it, it's spiraling around like this. You would think stars, right, moving this direction as they're moving away from you, moving away would be a red shift. And stars moving towards you, right, in the spiral would be blue shifted. And that turns out to be the case. In our galaxy, the stars we look at, if they're moving away from us, they're red shifted. If they're moving towards us, they're blue shifted. But what's strange is you would think the same pattern would occur in other galaxies. Okay? Spiral this way should be red shifted. Spiral this way should be blue shifted. So about half should be red shifted and about half should be blue shifted. You would think, right? But that's not the case. When Edwin Hubble was looking at other galaxies, he'd see that most of them are actually going red shifted. Okay? Like an overwhelming number are all red shifted, meaning they're moving away. Okay, so how can that be? Is the galaxy, has it stopped spinning around, right? Is it no longer following that spiral? No, of course not. It just means the entire galaxy itself is moving away from us. And he looked at tons and tons of galaxies and found that to be consistent. All the galaxies are moving away from us. So is it just a weird happenstance that everything happens to be moving away from the Milky Way galaxy? No, that doesn't make any sense. Not only are they moving away from us, but all the galaxies are moving away from each other. Okay? So all the stars and other galaxies are redshifted, meaning all the galaxies are moving away from us, and they're all moving away from each other. So that only leads to one conclusion, and that is the idea that the universe is expanding. Okay? So that's the big idea we talked about this week, is that the universe has to be expanding in order for all of this to make sense with Edwin Hubble's measurements. Okay, so because of this redshift, because of these standard candles, etc., we know that the universe is expanding. Okay, but if you think and reverse that process, well, if the universe is expanding, then it must have been smaller before, right? And if you keep rolling back the clock, well, then it was smaller before that, and smaller before that. So if you just keep going backwards and backwards, right? If the galaxies were this far apart right now, that means before they were this far apart, before that they were this far apart. Keep doing that, keep doing that, keep doing that, you get to the conclusion of the Big Bang. Okay? If there's no reason that you can't just keep reversing that process and realize that the universe at one point was in one very dense spot. Okay? So that's what we're going to talk about next week, is what is the Big Bang? Why do we think it's true? What evidence do we have for it? Okay, how could all the material and matter be in one spot in space at a single moment? Okay, and then expand. Okay, and that's what we'll discuss next week. But until then, ponder on that. Ponder on why expanding universe means that the Big Bang is possible. And I'll see you guys next week.